This is Unit 4 Modeling, and this is day number 3, Systems of Inequalities. This is really a review of something that should have already been covered in 8th grade math and Math 1. So what's going on here? We're going to solve these systems of inequalities. Since these are systems of inequalities, a lot of times we're going to have infinitely many solutions. We can represent the solutions really effectively with a graph, and that's what we're going to be doing here. The first thing to do when you're solving a system of inequalities is to graph each inequality, and in doing that we're going to graph their boundaries is what we're going to do, which is the line, in this case, 2x minus 3. So what I'm going to do for that one, I'm going to go to negative 3, the y-intercept, and then I'll rise 2, run 1, since that's my slope, and get me some points out through here. And go ahead and graph that line. Alright, just going to use a blue one. That was actually horrendously thick. Let me actually kind of shrink that down a little bit. Okay. That'll work a little bit better. Now, after I've gotten that boundary done for the first one, since the inequality is equal to this boundary is a part of my solution set. So I'm actually going to leave this as a solid line to show that it's part of my solution. Also, the function is greater than or equal to, so since the y values need to be greater than or equal to this boundary, it's going to be everything above this boundary. To know for sure, you could actually do a test. You could test like the point 0, 0 in the inequality, and it does come out as true that 0 would be greater than or equal to negative 3. So that's the reason why 0, 0 is part of the solution set for this first one. Now I'm going to do this process, but for the second one, I'm going to do this in red, okay, or purple as it is. All right, so graphing the boundary, plus 2 is my y-intercept. Since my slope is 1, it's down 1 over 1. And I'm going to go ahead and get this graphed out. Now on this one it's a little bit different because it was not equal to the boundary. Okay. With this one, what we've got is an example where when it's not equal to, what I should actually have here is a dashed line, because the boundary itself is not actually part of the solution set. So I'm going to go back through here and just make it a dashed line, really. Alright, that'll work just fine. Now, as far as that boundary goes, since y is less than negative x plus 2, I'm actually going to be graphing everything below. When I do that, I can see that the overlap is actually going to be right over here on the left-hand side of the intersection. So that's where my answer is actually going to be. So I'm just going to quickly shade that in. And now I know that any point within that region is actually an answer. So I'm going to actually go back and kind of erase this extra shading I had going on where it did not overlap. Now what I would know is that anything that's highlighted right here in the shading is a solution. For instance, negative 3, 0 is a solution. Any of these points are solutions. The tricky ones are on the boundaries themselves, and that's the reason why we made a difference in the kind of lines that we were using. So a point like 1, negative 1 that lies on that blue boundary, that is a solution because the boundary is solid, and it is underneath the purple line. A point like negative 1, 3 right here, while it is on the boundary, it was not equal to that boundary. So negative 1, 3 would not be a solution to this system. It wouldn't work for both inequalities. Meanwhile, the point of intersection would not work for both inequalities because one of the inequalities was not equal to, the purple one was not equal to. So the point of intersection here would not be part of the solution set. Only everything that's in the shaded region and anything on the blue line that's down here, nothing above the purple line would work. There's my solution set, any of these points. All right, so if you're watching this for the first time, go ahead and take a look at this one. Just hit the pause button and give it a try. And what you should have gotten is this answer right here, that this would be your solution set. Making sure that I have the correct boundary dashed. This boundary is the x plus 1. That was dashed. The first one, 3x minus 3, that one was solid. And then you have your feasible region in the top corner right here, due to it needing to be under the solid line, but above the dashed line. And that's my region. All right, moving right along, let's give it another try. So if you'll just hit the pause button and see how this one goes. This is a unique kind of situation here. All right, if you did that one and got them graphed out and shaded, what you would see is this would actually be a special situation. Because the graphs never overlap, this one actually has an answer of no solution. I would not really represent the answer with the graph. I would actually state that there is no solution. There is not a single coordinate anywhere that meets the conditions of both inequalities due to them never overlapping. Now, you might be like, oh, okay, so when there's parallel lines, it's always no solution. Not the case. With inequalities, you could have parallel lines, but maybe the graph is in between them. That might be a case where it's not no solution. Or if they were both greater than, if both the lines were greater than, it would be just this graph right here would be your solution. So sometimes you do have a solution when you have parallel boundaries. But in this case, with these parallel boundaries, there are no solutions, so I would actually make a note of that. All right, this last one, this really applies to where we're taking this, is where we're going to have feasible regions coming up next in this unit that we have to describe with inequalities. And this is an example of one. So what's going to happen here is I'm actually going to solve for y on each of these, get them into y equals, so negative y is greater than or equal to negative 2x minus 1. So y is less than or equal to, remember you got to flip your sign there when you divide by negative, 2x plus 1. Right here, y is less than or equal to negative x plus 4. Subtracted my x over. And on the last one, 4y is greater than or equal to negative x plus 4. And divide by 4, I get y is greater than or equal to negative 1/4 x plus 1. And what's going to happen is I'm going to graph every one of those and see where the feasible region is. It is going to be a closed off region on this one. It's actually going to be a triangle with 3 boundaries. Sometimes they're not bounded though. Sometimes you actually have an unbounded region. So starting with this first one, 2x plus 1, y is less than or equal to 2x plus 1. There's my plus 1. Let me use a different color here. And rise 2, run 1. And I quickly see my region there. And I'm just going to kind of make a quick note that it's going to be anything below that line. Okay? And now I'm going to graph out my other stuff. Moving on to the next one, I'm going to use blue here. Y is less than or equal to negative x plus 4. There's my plus 4. And here's my boundary. And I'm going to go ahead and get that graphed out. And again, since y is less than or equal to, I'm just going to make a quick note that it's anything below that. So I can see that right now I'm within this region right here, which is currently unbounded. This last inequality is actually going to bind the region. So y is greater than or equal to negative 1/4 x plus 1. I'm going to use black right here. So plus 1 down 1 over 4. And going to go ahead and get this graphed out. And it's going to be anything above that boundary. And so since it has to be above that boundary, I'm actually going to have a bounded region, which is right here. There's my triangle I was talking about earlier. Just because you have 3 boundaries doesn't mean it's going to be a bounded region. For instance, if it had been less than this black line, then it would have been an unbounded region down below here with just 2 vertices. But now we do have a bounded region for what we've got on this problem, and it wanted the vertices. So my final answer here is the vertices of the figure is 0, 1. We also have a vertex at 1, 3. and also at 4, 0. And you'll see next week that we're really interested in where these vertices are for our regions, whether they're bounded or unbounded. That's where this is going to be actually applied to something in the world. So more to come on this.